As you can see, previous presentation was by Jesus Toribio. Mine is about the same thing, perlite matrix components. And as you can see, these perlite microstructures are very complex to tackle when you are going to try to assess if a fatigue fracture is in place. So, since many important fractures happen, think of cable cars, ropes that break, we have to find a very simple method to assess this type of fractures. We use the two types of steel. One is a rail steel with an average composition of 0.7 carbon. And we also went back 40 years to what we have been done on a C85 steels. Well, it was a 1085 because it was bought in America, in the United States in America. And in both cases, you can look at the composition, nothing spectacular. When you use a scanning electron microscope to look at the microstructure of perlite, you have to go to very high enlargements to understand something. And this is a surface, a metallographic surface etched with metal 2, and so is the ferrite that is consumed, and the cementite is the one that extols. So here the white platelets are the ones of cementite, but you have to go to 25,000 X to really see something. Also, perlite has a very dangerous, as I say, brittle to ductile transition curve. Only at temperatures above 200 degrees C, you can see some real ductile fracture. At a room temperature, about 20 degrees C, and also in the region between minus 10 to plus 50, the situation of the energy absorbed is just the same, very low. And while taking into consideration various curves, you see that you have a real transition when you look at a 0.15 carbon steel. But when you go to a 0.45 and then to a 0.85, you get even at the highest temperatures, very low absorbed energy. Please consider that R means farnas annealed. It is the Italian ricotto. When you go at high temperatures and look at the fractographs of a C85 steel, you can see that this is for sure a ductile fracture surface. And if you go to higher enlargement, you can see that C85 steel has got ferrite crystals that have been elongated. Cementite crystals are in the bottom. They appear very dark. And also in the case of a C45 steel, ferrite isn't able to develop a fully ductile fracture because of constrained ductility due to the fact that it is interspersed with very high colonies of perlite. With modern SEMs, you can see better what happens at 220 degrees C when you have a sharp PV impact broken sample of rail steel. But when you go to low temperature, the same steel, you can really see that is definitely a brittle fracture, brittle cleavage fracture. And this is at the maximum, as I can say, at the maximum speed. When you reduce a little bit the speed, you still have some, almost all cleavage fracture. And so you can be sure that at room temperature, you should see cleavage fracture, very brittle. But if you have fatigue, then something happens. This is the fatigue. And for sure, this is not a very brittle surface. And you increase, and you can see that again, in a different way, ferrite crystals extols from the bottom. And if you look at the very high enlargement, you can even see striation on top of a ferrite lamella. So what's your conclusion? If you take a high carbon steel component that has been broken at room temperature or at a slight different temperature, and if you discover that there are some ductile fracture features, you have to conclude that that was a fatigue fracture, which makes things very simple. You work at not so high enlargement because sometimes the samples have not been prepared properly. They have been oxidized by the environment, and you look for features. Do you see some ductile features? It has been fatigue. Thank you very much.